Hello dear students, so we are going to see here about what are the other solutions for overfitting in this particular topic. So the second type of solution to overfitting that I can talk is about regularization. So you will come across regularization in a lot of codings when you will be doing lot of work on neural networks, whether it may be CNN, RNN. So regularizations is what something which you will be working on. Okay, so that is one of the technique that will be helping you to avoid any type of overfitting into your particular model. So when you're designing a network model with different number of layers and different types of sizes, then what is the initial function hypothesis space that could be provided for the optimization algorithm? Every machine learning or a deep learning program has got a hypothesis space. So what is the initial function hypothesis space that can be provided for the optimization algorithm? But the actual capacity of the model can change as your network parameters are getting optimized and updated as per your optimization algorithm. So the capacity of the preceding model can be simply measured through n is what we are calling here, and this is one mathematical representation that you can present over here. So you have got y is equal to beta naught plus beta 1x plus beta 2x square, so on. So you can see that as it is increasing with respect to the power of n, capacity of your model is increasing with respect to the power of n, and apart from this you also have some observation errors or epsilon. Correct? So that's the mathematical representation now that you have expressed in terms of your outputs and inputs. Now by limiting your sparsity of the network parameters, the actual capacity of the network can be constrained. So you have got different types of network parameters, right? So if you want to actually limit the sparsity of your network parameters, that means where your network parameters are actually very less in number. Okay, scantiness. Okay, so these constraints can be generally achieved by adding additional parameters, which we call them as sparsity penalties. These will be added to your loss function. So what is your optimization goal? Your optimization goal, the optimization goal, before you add up any constraint here, we will write it as you have got a loss function that you have got a loss function, right? And you actually have input and output of a particular model, correct? And you try to find out the loss between this applied activation logic and you whatever you get as f theta of x as your output, and that is your predicted output and your actual output. You would try to find out the loss function between both of them and you would try to minimize it, correct? So this is about your optimization goal, where your x and y belong to your training data set, correct? So your aim for optimization is to minimize this particular loss function that you achieve by taking out the difference between what is being predicted and what is actually present, correct? So what is this is before you add the constraint, okay? But then because of the sparsity or scantiness of network parameter, you want to add up certain sparsity penalties or some adding certain constraint that we call it. So what you are trying to do is you try to add up, this is your loss function which you try to minimize, and you try to add up this penalties or constraints that we call it. So we are representing that as lambda into omega of theta. So you can see theta is the parameters of your model, okay, and omega of theta is the function which is called as sparsity constraint function, and it is dependent on the network parameter. Lambda is going to be scaling factor to this particular sparsity constraint function. So what you do is to achieve the proper actual you can constrain the actual capacity of the network by adding up these penalties, sparsity penalties or sparsity constraint function that we call to this particular loss function. So this particular part is called actually as regularization. So The sparsity constraint of the parameter theta is achieved by constraining the loss function norm of the parameter. So norm of your loss function is what we take up, and this is the particular mathematical representation of that constraining function. So what you take is, you take say modulo of theta I and summate it over all the values of theta. Okay, so the goal of an optimization algorithm is to actually minimize your loss function, correct? But apart from that, if you have added constraint to your network, then its goal will also be to reduce this network sparsity omega of theta. So for that, you have this scaling factor called as lambda, which we also call it as weight parameter, and that is going to balance the importance of this loss function and omega of theta, correct? So next we are going to see how it does that. So if you are taking the value of this particular particular scaling factor lambda, weight parameter, then if it is large, then that means the sparsity of the network is more important. Otherwise, if you are taking smaller lambda, it means that training error of the network is more important. So based on that, you choose the value of lambda. So by selecting the appropriate value of lambda, you can get a better training performance, while also you will ensure about the sparsity of the network. So with these two into control, you are getting a good generalization ability. This particular method is called as regularization. There are three categories of regularization: L0, L1 and L2 regularization. Let's have a look what they are. So if I talk on L0 like regularization, based on the value of omega of theta, sparsity constraint function, we have got, based on, actually I can say, the order of omega of theta, you have got different types of regularization. So the first one being L0 regularization refers to the regularization calculator method by simply using L0 norm as per the mathematical equation shown onto your screen. So what is this modulo of theta of 0? It is defined as the number of non-zero elements which are present in that set of parameters. Theta is nothing but number of your set of model parameters. So under that, how many non-zero elements are there? That meant it is going to summate, and then it is going to give you the value of omega of theta. Now this constraint can force the connection weights in the network to be mostly zero, thereby reducing the actual amount of network parameters and network capacity. So you're trying to constrain your network, right? So that can be done by forcing your connection weights to be mostly zero. So see, the major disadvantage of this type of regularization, and because of it is not used in neural network, is that it is not at all derivable. So you all know that for optimization and for back propagation inside neural network, you require something which should be derivable. You should have a gradient, because we are working with gradient descent algorithm. So L0 norm regularization is not at all derivable. That is the reason that it is not used in neural networks. Now quickly moving on to L1 regularization. So L1 regularization refers to regularization calculation method using L1 norm. So you can see the change in the formula now. Now I have here summation of modulo of theta I over 1. So that is defined as sum of the absolute values of all the elements in the tensor. Now I'm talking on tensor. Okay, it's a big dimension now. So L1 norm is defined as the sum of absolute values of all the elements in the tensor theta I. So the other name of L1 regularization is lasso regularization. It is continuously derivable, and it is therefore widely used in neural networks. So this type of regularization can introduce a good amount of sparsity penalty term, helping you to constrain your model, as well as provide less amount of training error, thereby providing better training performance. So that's the motto of regularization, and that can be very easily achieved by using a lasso regularization or L1 regularization. So this is a simple implementation that I'm seeing. It's a simple mathematical calculation. I hope you are able to understand this. I am choosing here two random weights, W1 and W2, and I am going to simply reduce it towards its absolute value and add them together, and that will give me a loss leg here is nothing but omega of theta that I had been discussing so far. So this is my L1 regularization term. That's how I'll be calculating. Actually speaking, when you use Keras API and TensorFlow, you can just choose the type of regularization. No need of mathematically implementing any regularization, but this is just for your information. This is how to implement a L1 regularization. Now L2 regularization, as I told you, that depends on the order of the absolute value. So L0 may, there were no first order, it was zeroth order. So non-zero elements it was able to see, and weight parameters were all made zeros, and L1 may you could see that it could add the sum of all the absolute values of the elements, whereas now in L2 regularization, by the way, the other name of L2 regularization is ridge regularization. So in this you can see that here you have absolute value of theta I 2. So this is nothing but the sum of squares of absolute values of all the elements. Okay, so you can see how the difference is in the regularization. Again, because it is sum of squares of all the absolute value, you have got something in your hand which is non-zero, so it is continuously derivable, and it is also widely used inside the neural networks, correct? So this is again the small simple implementation. You can see the change in the implementation. In my previous code I have used only sum and absolute value, whereas here I am using TF square. I am not choosing ABS function because definitely squaring will give me a positive result itself. Okay, so that's how L2 regularization is implemented. So now what does this regularization achieve? So you are going to simply see a summary. In a standard least square model, it tends to have some variance in it, correct? So such model will not generate, it is not going to give you a better generalization for a data set which is different than its training data. I mean, for any other new sample, it is not going to give you a proper answer, proper prediction. That means its generalization is not that good. But because of regularization, it is going to decrease the variance of a particular model. But very important part is, although it is decreasing the variance, it is not going to increase the bias inside it. So this is very significant part of regularization. So tuning the parameter lambda, which is used in regularization, it is going to create a good impact on bias and variance. Okay, so as bias is as it is and variance is decreasing, generalization will be good. So as the value of lambda rises, it reduces the values of coefficients, and therefore it reduces the variance. Now till a point, if you are increasing lambda, it is beneficial, okay, unless and unless and until it is reducing variance in a proper value. But you have to also make sure that it does not avoid, you have to also make sure that reducing variance will also avoid your overfitting. And most importantly, because you are not affecting much to the bias, you are not going to lose any important properties inside your data. Okay, but after certain value, what happens, you have to be very careful. You cannot just keep on increasing your order of lambda. So that's why, because the model starts losing some of the important properties. That means, in other words, it is decreasing bias, but then it gives rise to increase in it decreases variance, but it gives rise to increase in bias. So once that happens, model will become underfitting. Okay, so you have to be very specific while you are choosing your value of lambda. Lambda should not be too high that variance start decreasing but bias gets increasing and it leads to underfitting. But lambda should be very carefully selected so as it can only reduce the variance, and keeping bias as it is, then it gives a proper proper fitted model, avoiding overfitting. It gives you a good results. So that was about regularization and importance and different types of regularizations.